So let's continue our discussion of waves, specifically the case of sound waves. And here you can see in this speaker that as this particular cone here, be it made of carbon or paper or whatever modern speakers choose for their material, this will vibrate in and out based on electrical impulses provided to it, and then vibrate the air, causing sound to be conveyed. And when we're dealing with sound, of course, we're dealing with one of our longitudinal waves. And in that case, that means this is compressions and rarefactions. The sound waves themselves are being vibrated back and forth. And as you can see here, here's our compression, and here's some of our expansions or rarefactions coming to the human ear, which then vibrate and get translated into sound. Now, in this particular case, we can see that we can model this using a longitudinal wave. So when we're looking at transverse and longitudinal waves, we can very much model the compressions and rarefactions as a harmonic term. So we can still express our sound wave in terms of sine, cosine, and the usual harmonics. And when we look at interference of sound waves, it can be conveyed in the same way as we were looking at, say, vibrations down a string. We're still dealing with a harmonic pattern. And here's a bit more of an animation dealing with sound waves moving through what's referred to as bulk media. Usually, bulk media refers to a fluid, that being something like water, so like whale song moving through the ocean as a sound wave, or by music or voices moving through the air as a sound wave. This additionally could be in a solid such as rock when we're dealing with something like earthquakes, then the rock itself is conveying waves of this nature and looking at vibrations through solid material. But our sound waves are longitudinal waves, and we can model them as harmonic transverse waves, as shown here. So as we discussed before, we'll be looking at compressions and rarefactions. So as our sound wave travels through the air, elements of the air get disturbed from their equilibrium positions, and that causes changes not only in the position of particles in the air, but also in the density of the air and the pressure of the air. And when we're talking about the waves, as we said, they are just waves. So we can look at our previous material to really see how waves behave. And we can apply that to our cases of sound waves. So here's just a bit of a reminder when we were looking at periodic waves. When we look at the displacement, we're looking at some maximum amplitude times some cosine term. And here we're looking at kx minus omega t, our familiar wave number, angular frequency, and time. So looking at gas pressure, delta P, we can see our periodic wave. The pressure here will be delta P equals delta P max, the maximum pressure, times sine kx minus omega t here. Essentially, this pressure will move in a periodic fashion, as will the displacement, which should make sense, because the pressure will follow the displacement of a particular particle. When we're talking about pressure, we can also relate this to what's referred to as the bulk modulus. Now, the bulk modulus is a measure of the material and how it responds to pressure waves and how much, essentially, the density of the material. So here we can say delta P, our change in pressure, will be equal to B, this bulk modulus, times the maximum displacement times K, where B here is the bulk modulus of the material, so B is given by negative delta P over delta V over V, where this is a change in volume over the overall volume. So as we said, sound waves are considered to be displacement or pressure waves. A pressure wave here is 90 degrees out of phase with our displacement wave. And this should make sense, as it's essentially the pressure wave that gives rise to the displacement. So pressure is maximum when the displacement wave is at a zero. And this diagram here shows our displacement. Here's our displacement starting out of phase with our pressure wave. Here, delta P, our pressure is at minimum, and here, when our displacement is minimum, our pressure is maximum. Minimum displacement, maximum pressure. Minimum pressure, maximum displacement. They're perfectly out of phase by 90 degrees. So when we talk about speed, this is a mechanical wave in the same way as the mechanical waves that we've discussed in the past with particular waves moving down strings. And the speed of a mechanical wave, doesn't matter if it's transverse or longitudinal, really depends on the inertial properties of the medium that it's in. That's how well they store kinetic energy and translate kinetic energy, but also how elastic they are. So when we're talking about sound waves, as said before, you can move a sound wave through solid material if it's the right frequency. As such, the inertia of the body, the actual inertia of something like the Earth when we're passing earthquake waves through it, S and P waves, will be quite different to something like that of the Earth, of the atmosphere. So here we're looking at that inertial property, and delta P, our change in pressure, will be equal, well, the change in momenta here of an individual particle will be equal to m delta v, where this is a velocity, and this will equal to pv times v in the x direction, a delta t. Now, the important result of this is a relationship that takes into account velocity and b, the bulk modulus. And remember, our bulk modulus came from that previous expression of b is negative delta p over delta v over v. So our velocity is the square root of tau here over mu. This is the elastic constant over an inertial constant, which is provided for any one particular material. This will equal to b, this bulk modulus, divided by the density of our material square rooted. And this b factor will pop up quite a lot. So the speed of sound waves in a medium depends really on the compressibility, as said before, and the density of that medium. Hence the difference between sound waves in water versus air. Whale song cannot be readily heard through air, but it can be easily heard through water. So this expression really gives us the speed of all mechanical waves through some kind of atmospheric material. So as said before, this is the change in momentum of our gas, and if we set the impulse side of the equation equal to the momentum side and simplify it, we can get the speed of sound in our gas as b over rho rooted. The other thing about the speed of sound is it also depends on the temperature of the medium. This means that the speed of sound at sea level, essentially at the ground, is often quite different to the speed of sound at higher altitudes. Meaning when aircraft break the speed of sound on a routine basis, they're actually breaking a lower speed of sound than they would be if they were at the surface of the planet. So, in terms of gases, here we can see a sound speed, v, will be equal to 331 meters per second times the root of 1 plus temperature in Celsius over 273. This relating to the Kelvin scale, which directly accounts for the thermal motion of materials, of particles in a material. So 331 meters per second happens to be the speed of sound at t equals 0 Celsius. And all of these velocities are then calculated relative to that, where Tc here, as said, is the air temperature. If you need a velocity at a particular temperature, you can simply take this formula and substitute in your temperature in Celsius. So the speed of sound is basically about 331 meters per second in air. This is at the 0 Celsius line. This changes by about 0.6 meters per second for every degree Celsius away from 0. So you could in your head guess that to be about 1 meter per second for every increase in degrees Celsius, but calculationally use 0.6. We do have two terms, and we'll talk about these in a bit more detail later on. Subsonic, this is for objects moving slower than the local sound speed, and supersonic, this is for objects moving faster than your local sound speed. And since sound speed is relative to rho, that means you could see a variety of speeds of sound. Those, say, underwater, those at sea level, those in the upper atmosphere, or even those in a nebula deep in space, which even though it's at very, very, very low pressures, will have a local sound speed, which really relates to how quickly a shock wave could be translated through it, if we're talking about systems which are exceeding the speed of sound. If we start to deal with Mach numbers, then this system really kicks in once you start to exceed the speed of sound. So when we see something like a sonic boom, this is a pressure cone caused by an object traveling faster than the local sound speed. So pressure, amplitude, and displacement are really related by this equation. Delta P max is equal to B, our bulk modulus, times our maximum displacement times K, which we've seen before. Gas pressure measurements, though, are often easier to obtain than the bulk modulus. You can just easily get these from some kind of anemometer device or from a mercury barometer or something like that. Getting a measure of B can be a bit more difficult. Consequently, we often find ourselves having to convert between P and B. B, of course, can be expanded, and this equation becomes a little more normal for a situation when you're looking at a specific density and velocity. So delta P max equals rho V omega S tends to be the more frequently used equation of these two, even though they are essentially one form or another. So we talked about sound speed in various media, and you can see these particular media. Here we're looking at liquids at 25 Celsius, gases at 0, and we've got solids over here. Temperature tends to be less of a factor with these solid objects because when you start to actually significantly affect the particulate motion, they start to melt. So here we're looking at hydrogen, and as you can see the sound speed is much higher in something like hydrogen than it is for oxygen, and you can see 317 at 0C, very much like it is for Earth's atmosphere. Of course Earth's atmosphere is an oxygen-nitrogen mix, but oxygen and nitrogen tend to be about the same in their responses to sound. And as you can see, the speed of sound in these media, we're looking at much higher sound speeds here and here for solids and liquids than we are in gases. Now, when we talk about the speed of sound, we obviously know that vehicles have exceeded the speed of sound, especially aircraft, which now do this on a very regular basis. Fighter jets regularly exceed the speed of sound, and the former Concorde, which used to run transatlantically from Britain to the USA, exceeded the speed of sound with passengers on a regular basis. The first person to break the speed of sound, who died only last year, was Brigadier General, as he died as Chuck Yeager, who broke the sound barrier in 1947. I do mention here as a historical aside that he was the first to break the sound barrier and live. It was rumoured that previous pilots had broken the sound barrier in uncontrolled dives, and this is quite possible. Unfortunately, most people who actually broke the sound barrier before Mr. Yeager here wound up dying due to the fact that they lost control of their aircraft and crashed. So Chuck Yeager one of the great heroes of exploration and pushing the boundaries, who actually broke this sound barrier chewing gum with a broken arm, which is relatively impressive. And here's a modern aircraft breaking the sound barrier, and as you can see, there's this pressure cone that we'll talk about later that occurs as you break the sound barrier. Now, as I said, if you're at much higher altitudes, the speed of sound tends to be relatively lower, and then therefore a little bit easier to break due to its reduced density. That doesn't mean that no one has broken the speed of sound at ground level. The Thrust SSC car actually broke the speed of sound for a car, for a vehicle driving on the ground, and that required a lot of very, very specific engineering, and it was a very, very difficult task. And as you can see, here's the car, and you can actually see the pressure wave built up ahead of this car, pushing the dust on the salt flats. So we've talked about the speed of sound, and we'll talk about that a little bit more as we go. But what about the power of sound? And remember, power is essentially the energy per unit time that's expended. Well, power of sound really relates to the rate of energy transfer in our wave. And power will be equal to F times V, our force times the velocity of our wave. If we expand that for both force and velocity, what we'll see for power for one oscillation will be 1/2 rho AV omega squared S squared. So the challenge with this particular set of material is not so much the application of these formulae. These formulae tend to be things that you can just put numbers into and get an answer out. It's where to use what formula that's really the question. And this really comes down to that shopping list method that I use in classes. Stating your variables very, very clearly at the beginning of a problem. Saying, what do I have? What can I easily find? And then finally, how can I arrive at an answer? And that will help you select the correct equation in order to complete your task. As well as power, we also have intensity, and this is the rate that the wave's power this is the intensity is the wave's power per unit area, and that's the rate at which the energy is transported 90 degrees to the wave direction. So really this is going to be some measure of how much power we have from the previous equation over how much area is it spread out. So essentially I, our intensity here, is going to equal the average power of our wave over an area. This will equal 1/2 rho v omega s squared, which will give us delta p squared over 2 rho v. And this is probably the more condensed and more useful particular formula. Now, the intensity of a wave really does dictate to a degree how strong that wave is. What's the intensity, say, from a sound that you're hearing will be reduced with distance, and as such will be a lot quieter. That's why objects in a distance are quieter than objects close to you, as their intensity is reduced. Now we'll talk about hearing shortly. But the faintest sounds that a human can hear are at about a frequency of 100 Hz. Now, that gives us an intensity of about 1 × 10⁻12 watts per square meter. So that's a power spread out over an area. And this is what's referred to as the threshold of hearing. Let's take a look and determine the pressure amplitude and the displacement amplitude associated with this lower limit. And this really is employing the equations we've seen in the last few slides. So if we go back and look at our relationships carefully, we'll see that delta P, that is the pressure, the change in pressure of our wave, will be equal to √2 of PVI, where P is our pressure, V is the velocity of our wave, and then we're looking at I being the intensity of our wave. Now I'm introducing a few values here for typical sort of atmospheric cases, and you would be given these if you expect to use this formula. So this will be 2 times about 1.2 kilogram per cubic meters times about 343 meters per second for the speed of sound here, times 1 times 10 to the minus 12 watts per square meter given here in the question. This will give us about 2.87 times 10 to the minus 5 newtons per square meter. This means S max, the maximum displacement, will be delta P over rho V omega. Substituting in once again, delta P here is going to be the number we calculated in the first part, divided by the values that we had to start with here. That'll give us 1.1 times 10 to the negative 11 hertz meters. So that power will actually be distributed equally over a spherical area. If we're actually looking at the power of our wave, we have to look at this wave moving through three-dimensional space. That means our wave intensity from a source is essentially going to be the power divided by the area of a sphere, 4 pi r squared. So power is simply divided by over spherical area. This, of course, is being pointed out because this is an inverse square law, something you'll see later for light. This is essentially a wave spreading out as an inverse square, getting further apart and more rarefied as it moves through the atmosphere. And the reason we care about intensity, as per our previous example, is this is kind of a measure of loudness, which is a word that sounds a bit clunky. Now, intensity is really related to the energy that our wave is carrying with it, which of course does relate to how loud our wave is. But loudness is sort of a human perception of the actual physical intensity. So it's sort of the human embodiment of physical intensity of our wave. So loudness is measured on what we call the decibel scale, which we'll discuss. Now, when we're talking about a propagating wave from a point source, as said, this comes out as a spherical wave, and each surface of constant phase gives us a wave front. So the radial distance between wave fronts essentially becomes the wavelength of our wave, lambda. And there's our spherical wave from a point source at the center propagating outwards as 1 over r squared, where the spacing between each of these spheres would basically be a wavelength each, a lambda. So if we were to actually measure each of these wave fronts with a device, a pressure device, we could actually figure out the wavelength of the sound wave through the air. So let's take a look how we can use this. And this is a typical example of looking at the intensity of a sound wave. Here we have a point source and it's emitting sound waves with an average power of 80 watts. That's 80 joules per second. Let's find the intensity 3 meters from our source. Remember, our intensity was power per unit area. So I is our power over 4 pi r squared. Relatively simply, r is 3 and our power is 80. So we can just divide these out and get 0.707 watts per square meter. Now, quite often, you'd like to find out what the intensity is at a specific location. So let's find the distance at which the intensity of the sound is about 1 times 10 to the minus 8 watts per square meter. So here, if we rearrange, our distance is going to be power divided by 4 pi times the intensity. Substituting in, we had 80 watts over 4 pi times I, which is 1 times 10 to the minus 8, which will give us 2.5 times 10 to the 4 meters. as quite a long distance. So at about 25,000 meters or 25 kilometers away, you would still detect this particular sound wave, and it would have intensity here of 1 times 10 to the minus 8 watts per square meter. So this would be quite a loud event, as this would be sort of on the verge of not being heard by human ears. So in terms of sound level, the thing is with sound, very much like light, that humans can actually hear, experience and interpret sound. Sound may be a more important communicator in a lot of cases than vision for a lot of people. And as such, we can detect a range of different intensities. And the range of intensities we can detect is quite large. Because of this, we need to condense our mathematics down and condense our scale in terms of using logarithms. So using base 10 logs, our formula here to determine the intensity will be beta is equal to 10 log I over I0, which is equal to 10 log I over I0 here. This is in decibels. And that's the scale for determining essentially human perception of sound in decibels. When we're talking about the human ear, of course, remember we're looking at sound waves coming in, hitting the human ear, which is shaped to focus sound waves. So it will gather sound waves, put it through the ear canal, where the eardrum will be vibrated in and out. There is what's referred to as the hammer and the anvil in here, which will essentially vibrate together and create sound waves, and then you can convert this to nerve impulses, which are sent to your brain, allowing you to actually interpret sound waves. So the outer ear collects the sound, the middle ear amplifies it, and the inner ear really converts it into sound, into nerve impulses. And that's how we interpret our sounds. So here's the equation mentioned before. Here, beta is essentially our value in decibels. I0 is some reference intensity, which is set at the lower limit of human hearing at about 1 times 10 to the minus 12 watts per square meter. Obviously, this will vary based on the individual person, experiences, hearing damage, age, things like that. But a healthy human should hear at about down to about 1 times 10 to the minus 12 watts per square meter. Beta is our sound level in decibels, of course, and being a logarithmic scale, this means that beta will increase by 10 decibels each time I increases by an order of magnitude. So B is equal to 40 actually corresponds to an intensity 104 times this standard reference level. And here's the kind of scale you should expect to see in terms of hearing. People whispering here, this is in decibels, of course. People whispering at about 15 to 25 here for purring cats. Your average home sitting at about 50. Then we've got vacuum cleaners, noisy public places at about 80, and then this goes onwards up to things like mowers and chainsaws at 100 to 115, being sort of uncomfortable. And then we have a pain threshold for human hearing of about 120 decibels. Jet planes at about 150. So this is kind of the scale you should expect to see. So industrial noise here at about 110, and conversation, snoring, etc. It should be pointed out that there are quite a few noise restrictions, especially in industrial locations where hearing protection must be worn. Hence the fact that industrial noise is accepted to be at about 110, and hearing protection should be worn when going being sustained over about sort of 80 to 90. So typical questions that we might see: What's the sound level that corresponds to an intensity of 2 times 10 to the minus 7 watts per square meter? So, employing our equation, beta will be equal to 10 log I, so over I0, so this will be 10 log 2 times 10 to the minus 7 over 1 times 10 to the minus 12 watts per square meter, giving us 10 log 2 times 10 to the 5, which give us about 53 decibels. A doubling of this value, a doubling in loudness, will actually be compared to about an increase of 10 decibels, because remember this is a logarithmic relationship. So the sound level in decibels really relates to a physical measurement of sound strength. There is also a psychological measurement of sound strength, which we won't really attempt to quantify since this is a physics class and we don't want to go too far down the psychological road here. Humans essentially can calibrate their personal response to sound by their experiences and their usual surroundings. If you live in a very loud home, for instance, or work with very loud machinery a lot, then what you consider loud will be reduced compared to a lot of other people. If you spend a lot of your time in a library or a lot of time by yourself, then going into a crowded room with a lot of people talking or being exposed to a lot of industrial machinery will feel loud to you, possibly louder than it might do to somebody else. Consequently, when it comes to loudness, there's a complicated relationship between loudness and frequency. And the frequencies that people experience can often have different effects upon them and the sound level they perceive. And as you can see, here we're looking at various frequencies from 0 to 220, from 1 to 100,000, and sound levels here in decibels from 0 to 220. So up here, this is infrasonic. This is way above where you would normally be. But here are infrasonic frequencies here. Here's the sonic frequencies, and here's ultrasonic. So when we start to get to ultrasound, these are frequencies that humans cannot actually register, but creatures such as bats can. The black area here is the average human response to sound. The lower curve is our hearing threshold, and the upper curve is our pain threshold. But generally, when we're looking at our situation, high frequencies mean more vibrations hitting your ear. The pitch of a sound is how high or how low a sound seems to be. When we're talking about frequency, a normal healthy human can hear from about 20 Hz to 20,000 Hz. And this is quite a range, 20 Hz to 20 kilohertz. But humans are most sensitive from about 440 to about 7 kilohertz, 7,000 Hz. Ultrasound tends to sit about 20 to 100,000 Hz. And infrasound, the other end of the spectrum, low frequency, so this is high frequency, low frequency would be 20 to 200 Hz. So when we're dealing with things such as ultrasound, frequencies greater than 20,000 Hz, of course, dogs can hear to about 35,000, bats can hear over 100,000 Hertz, and medical diagnosis equipment, people having ultrasounds done for medical reasons, either to image, say, tumors or any internal problems, or indeed pregnant women having ultrasounds to actually image a baby inside them where radiation would be damaging. Infrasonic sound, this is the kind of thing where we're dealing with very heavy machinery, earthquakes, such things as that can usually be felt by humans as opposed to actually heard. So let's take a look at another example. Here we have two identical machines positioned the same distance from a worker. The intensity of the sound level delivered by each machine at his location is 2 times 10 to the minus 7 watts per square meter. And this is the typical thing that can be done by health and safety workers when they're attempting to make sure that people are not exposed to damaging sound levels. Let's find the sound level heard by the worker when one of the two machines is operating. So in decibels, beta will be 10 log 2 times 10 to the minus 7 over 1 times 10 to the minus 12 watts per square meter, as usual, our reference intensity, and that will give us 10 log 2 times 10 to the 5, or 53 decibels. So this is the sound level expected at his location when one machine is operating. Now what happens when we switch on the second machine? Well, essentially we're going to repeat the previous calculation, just now with the intensity multiplied by 2. This means we will see 10 log 4 times 10 to the minus 7, 2 times 10 to the minus 7 times 2, over our reference intensity, giving us 10 log 4 times 10 to the 5, or 56 decibels. Now, if there's a lot of other machines they want to fit into this space, how many machines do we need to be running at that same distance from this worker to double his loudness? Remember, our loudness is kind of a psychological response, but generally doubling loudness increases your sound level by about 10 decibels. So to get to approximately 2 times the loudness, we have to correspond to a sound level increase of 10 decibels. So 10 machines have to be operating to double his loudness. So here, if we take beta 2 minus beta 1, delta beta essentially of our loudness is 10 decibels. This will be 10 log I2 over I0 minus 10 log I1 over I0. This will give us a ratio of the log of I2 over I1. So that will give us an I2 of 10 times the initial intensity. So 10 machines.
So let's look at a particular case involving sound. In this case, the phenomenon of musical sound. Now, music, of course, is a human concept, and this concept really relies on receiving patterns and deliberate pitches of sound to create some kind of musical melody, some kind of sound. So, sound quality really describes different levels, differences of sounds that have the same pitch and loudness. And music really has to have a pattern in order to consider it music, despite what some people will tell you when they want your money to buy music from them. Every instrument, and indeed every particular voice, has its own set of particular overtones. When we talk about musical sound, it's usually something set up by a standing wave, either in a pipe or on a string. There are, of course, electronic devices such as synthesizers that really do not use this kind of principle and generate electronic sounds. But in terms of physical instruments, we're usually dealing with a wind or a string instrument, or indeed things such as xylophones, where you have wooden blocks or steel bars which are struck and set up standing waves inside of those. Really following the kind of physics we've looked at previously involving travelling waves and standing waves in a system. Most instruments involve more than a single oscillating part to them. We're really going to restrict our treatment to the setup of a standing wave which will produce musical sound. The most basic kind of music probably comes from the setup of a pipe with two open ends. Indeed, there have actually been findings in archaeological sites of very ancient bone flutes where they've been hollowed out both ends and have a third hole put through the side in order to make musical sound. So this is a very ancient way of generating particular pitches of sound. And if you take a pipe with two open ends and essentially pass air through it, what you will do is set up a standing wave within that pipe. Here is the pipe of length L, and you'll end up with interference set up in here, giving you antinodes, nodes, an antinode at the end, antinode this end, and a node in the center. Now this will set up essentially the first harmonic here. As you can see, here's the two antinodes at the end and a node at the center. This is what's referred to as a fundamental node, or the first harmonic in this particular case. And this is probably the most basic way of setting up a tone or musical sound. So in terms of musical sound, you can of course continue to adjust the wavelength of your wave and end up with increased interference. So here we have essentially n equals 2, n equals 3, n equals 4, second, third and fourth harmonics, all increasing the number of nodes and antinodes that are set up within the actual chamber, within the pipe itself. This will of course give you a lambda of 2L over 2, or a lambda of 2L over 3 now for the third harmonic, and 2L over 4 when we're dealing with the fourth harmonic. So in order to set these up, the sound wave in the pipe of length L has to have a wavelength that's given by L is equal to lambda, the wavelength of the sound, over 2. So that lambda is equal to 2L. Of course, as pointed out here, the second harmonic requires sound waves of wavelength lambda equals L. The third requires a wavelength of lambdas 2L over 3, etc., etc., etc. for each order. If you have a resonant frequency for our pipe with two open ends, then you have to have it correspond to these wavelengths. And this is essentially what we were seeing here. Lambda equals 2L over n for each successive order, where n has to have an integer value in this case. We're talking about interfering waves here, and as such we have to have an integer value for these waves. So if we want to set up our resonant frequencies, lambda is 2L over n, where n is the order we're dealing with. N is referred to as the harmonic number, and in terms of our sound speed corresponds to this formula. F is v over lambda, a formula for the velocity of a wave that we've seen previously. Substituting in here, we can say now for lambda here that we'll end up with nv over 2L. Essentially substituting in for lambda means we've got 2L over n, and the n winds up being multiplied here. So v over lambda gives nv over 2L. And this is just another form of the same equation that you can use. Now when we're dealing with our musical sound, we have one open end. So some of the standing wave sound patterns can be set up in a pipe with only one open end. Across the open end you always have an antinode here. Across the closed end there's a node. So as you can see from these diagrams, here's the closed end of our pipe on the left, and here's the open end on the right. You'll set up a wave as such. Here you can see how much of the wave actually exists. It goes to n equals 1, and you have your antinode here. N equals 3, 5, 7. So across the open end you have an antinode, across the closed end there's a node. The simplest pattern requires that the sound waves be given by L equals lambda over 4. So there's a limit to the length of the pipe that you can actually have. And here, using L equals lambda over 4 means lambda equals 4 times L. The next simplest pattern gives you a wavelength that's given by L equals 3 lambda over 4. So that lambda here is 4L over 3, on and on and on. So the resonant frequencies for a pipe in this case of length L with only one open end give you wavelengths of 4L over N, where again N is an integer value but now is only for odd numbers 1, 3, 5, etc., etc., as we're only setting up odd waves in this particular scenario. So when we saw a pipe with two open ends, we had this formula: lambda was 2L over N for N equals 1, 2, 3, blah blah blah, any number of values. When we're dealing with a closed pipe, lambda is 4L over N, and the numbers N have to be odd. So essentially, when we're looking at our resonant frequencies, as we said before, lambda's 4L over N for odd numbers. Harmonic number N must always be odd. This means our resonant frequencies that we saw before, remember we talked about resonance previously and what that really meant, a case of a driven oscillation here that continues to resonate in your system. F will be V over lambda again in our formula. Here V is going to be NV over 4L, essentially substituting in for lambda again as we did before, taking the N to the top gives us NV over 4L for N being 1, 3, 5, etc., etc. So this means that only odd harmonics can exist in a pipe with one open end. You can never use N equals 2 here in a pipe with a closed end. And that's worth remembering when you're looking at a particular type of instrument. And this is why most instruments end up with two open ends, one to blow in and one for air to escape from, as this allows you to set up numerous different types of wave within, and numerous different wavelengths, and of course corresponding frequencies. This also means that the length of an instrument reflects the range of frequencies that that instrument is designed to function over. The smaller the length of an instrument, the higher frequency that is produced. The greater the length, the lower the frequency. So think of something like a flute and the high pitch that comes from that compared to, say, the bass saxophone shown in this diagram, or a double bass. So for each instrument there'll be some overlap with its high and lower frequency neighbors, but generally bigger instruments, which we probably realize psychologically, tend to give deeper tones. Now when we're producing music, what you actually hear in most cases is something like a beat. Now when you're dealing with a beat, this is essentially a pulsing variation in the loudness of the sound coming from that instrument. And this is caused by the interference of the sounds at slightly different frequencies. And this produces these gaps in the compressions and rarefactions in your wave as they interfere, and essentially gives you a pulsing tone. It's not that the music being produced is produced in bursts. The music is produced in one long wave, essentially one long continuous string. It's the interference of those waves that ends up giving you these pulsing variations, these beats that you hear. So when we're dealing with musical sound, this is what's going on. Here we have two waves, slightly out of phase with one another. You can refer to the work we looked at previously in terms of how phase will affect these two waves being added together. They are the same amplitude, so this would not be a time to employ something like phasors, but you could look at the two individual wave functions here and compare them in terms of their simple harmonic motion and of course omega and amplitude, and you would find that you could put these two together and they will constructively and destructively interfere in different places. So combining waves A and B here will give you wave C. And this is something, of course, that you can see if you simply switch on the visualizer if you're listening to music on a computer. And you can see the waveform of the music itself as it bounces up and down. So, most music that you hear is not one frequency. That would be one long continuous tone. Most of the music that you hear is some combination of frequencies, an average of two combined frequencies, or often more than that if you think about listening to something like an orchestra working in unison together. What you also hear, as well as these frequencies, is a variation in the intensity of the sound. So you can put these together to compose a variety of different sounds. So you perceive both the frequency and the variation in intensity. That means you can pick up increases and decreases in slow wavering beats that repeat at the frequency of the difference between the two. So remember, we're talking about frequency here. Psychologically, people often look to the amplitude. In frequency, what we're looking at is the number of repeated waves per unit time. These, being slightly out of phase, combined together will give you this differing frequency. So this really is, as I said, a case of wave interference. And what you have here are two time-dependent variations in displacement due to the sound waves, both of equal amplitude, S1, S2. So we don't have to employ any complex mathematics here because their amplitudes are the same. S1 and S2 equal Sm cos omega t and Sm cos omega 2t. In this particular case, we're saying that omega 1 is greater than omega 2. Going back to our previous discussions, we can then apply our superposition principle, giving us a resulting wave of S, being S1 plus S2. Sm is equal in both of these waves, so can be factored out, giving us Sm cos omega 1t plus cos omega 2t. And this is an excellent time to think back as to how you would solve this particular problem. I really should play the countdown music here and go da, 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 da. Remember how to do this yet? Use a trig identity. And here the trig identity we will use is cos alpha plus cos beta, which equals 2 cos 1/2 alpha minus beta times cos of 1/2 alpha plus beta. So if we employ this trig identity, we will get a resultant displacement of S, which is equal to 2S cos, factoring out our omegas, 1/2 omega 1 minus omega 2 times t, times cos 1/2 omega 1 plus omega 2 times t. Where in this particular case, omega is going to be 1/2 omega 1 minus omega 2, and of course omega is going to be 1/2 omega 1 plus omega 2. That'll give us an S overall with time of 2S cos omega prime t times cos omega t. What does that actually mean though in terms of the musical sound that we're producing? It's all well and good causing two interfering waves to give us a value of S and satisfying an equation in a physics test, but what does that mean? This means that the maximum amplitude occurs whenever cos omega prime t has the value of plus or minus 1. If you're talking about a cosine function, this will happen with each repetition, twice. So cos omega t has an angular frequency of omega prime here, so the angular frequency of our beats, omega beat, is 2 omega prime. So the beat in terms of an angular frequency becomes this, 2 omega prime, or 2 times 1/2 delta omega. But as omega equals 2 pi f, the frequency of our beat essentially boils down to being delta f. What is the difference in the frequencies between these two particular frequencies that are quoted? And all we're doing there, of course, with omega being 2 pi f, is converting from an angular frequency to a linear frequency, as we've seen before. So, Dr. Horn, you might be saying, you ingenious polymath, where are we actually going with this? So, where we're going with this is talking about penguins, the typical kind of penguin you might see on your way to work every day. So, emperor penguins, it turns out, signal one another using exactly the process we've just been discussing, using a two-sided vocal organ referred to as a syrinx. Not a sphinx, that's something different involving people, human heads and lions, but a syrinx. Each side of this particular organ sets up an acoustic standing wave in the bird's throat and then uses its mouth as a pipe that has two open ends. So if you flick back to, in the PDF at least, to what we talked about before in terms of a pipe with two open ends, you'll realize that we have to look at here odd frequencies, odd orders. So if the frequency here of the first harmonic produced by side A is FA1 equals 432 Hertz, so 432 cycles per second, and the frequency of the first harmonic produced by side B is 3771 Hertz, what is the beat frequency between the two first harmonic frequencies and between the two second harmonic frequencies? So what we're saying here is emperor penguins actually signal one another by utilizing the interference of two different frequency but same amplitude waves. Thank a penguin for making them the same amplitude and simplifying our physics explanation. So thank a penguin today. So the beat frequency, as we saw previously, is going to be given by delta F, the difference in F1 to F2. For the first two harmonic frequencies, FA1 and FB1, this is going to give us 432 Hz minus 371 Hz, giving us 61 Hz. This is our beat frequency. Now remember from previous, standing waves in a pipe with two open ends will have to have resonant frequencies here of F equals V over lambda, N or NV over 2L for N equals 1, 2, 3, etc., etc. Where L here is unknown. We don't know the length of the pipe here. So the first harmonic frequency here, F1, will be equal to V over 2L, with the second frequency of 2V over 2L. If you compare these frequencies, F2 will be equal to 2F1. So F2 equals 2F1. The second harmonic of side A has a frequency of FA2 then equals 2FA1. And the second harmonic of side B will have a frequency of FB2 equals 2FB1. So here we're putting things in terms of the beat frequencies. So what we will find here is in terms of our beat frequency, we'll have FA2 minus FB2, which will be equal to FA1 minus 2FA1 minus 2FB1. Substituting in, we can say this will be 2 times 432 Hz minus 2 times 371 Hz, giving us 122 Hz. Now what does that really mean for us? That means when you're presented with a problem such as this and you are given two different frequencies, we can exploit this beat frequency to come out with a final frequency for the interference of our waves without having to actually employ the individual wave functions. That means if you were to listen to the song of a penguin song, is that a thing? At least a signal from a penguin. then you could actually determine the frequency using various scientific equipment such as an oscilloscope hooked up to a microphone, and you could then figure out the corresponding frequencies they were producing. So you would not have to have the complete wave function determined in order to make this calculation as we just did. And what does this really mean on the scale of things? This means that penguins can perceive these really large beat frequencies. Humans can't hear anything higher than about 12 Hertz. But we can hear the two separate frequencies. That means we can hear a certain sound come from penguins, but penguins hear a completely different sound compared to us. I don't know what they're saying. Probably something to do with food, or eggs, or maybe water. But the point being, we cannot communicate with penguins, but we can hear them. A phrase I never thought I'd say. Having finished with penguins, frequencies and music, let's take a look at a scientific effect. Let's take a look at the Doppler effect, named for Danish scientist Hans Doppler. In this particular case, with the Doppler effect, what we're looking at is a moving wave source. So I'm sure people have actually experienced this. You're standing in the street and a car comes down the street with its siren running, say a police car or ambulance, and as the vehicle moves by, you hear a specific pitch emitted towards you. As the object moves away, you actually hear a lower pitch. So you hear a high pitch towards you and a lower pitch as the siren moves away. Indeed, you could do this with an engine sound also, if you were to pay attention to it. This is the kind of effect that's used in things like weather radar. If you watch something like local news, they often come on and say things like, oh, we used our super mega hyper Doppler radar in order to determine the direction and speed of this particular storm, most of which those words mean nothing. All they really mean is, when they say it's like a hyper Doppler radar, what they mean is the accuracy to which they are deducing the Doppler shift of the frequencies being bounced back from that cloud is increased. So the more accurate it becomes, the better information you have about the range and about the speed of that particular object. So most of what they say there means very little. And as you can tell, I find it kind of irritating. So here's the kind of effect we're talking about. And as usual, I do not recommend that you set foot on train tracks in order to hear this effect. I am not responsible for any injuries incurred by listening to the Doppler effect. Just wanted to make that clear. So here we have a train, which will obviously be emitting a relatively low frequency sound. But we have two observers, hopefully on the sides of the train tracks. One in front and one behind. So, as they are both listening to a stationary train, the wavelength that's emitted by this train will be the same for both observers, both the one looking from the rear and the one looking from in front of the train. Now the train has started to move to the right. As it moves to the right, emitting the same sound, so if you were sitting on the train you would hear no change in pitch whatsoever. But the person on the right will hear a shorter wavelength, a higher pitch sound. The person on the left will hear a longer wavelength, a lower pitched sound. And that is the Doppler effect. If a source is moving towards you, you will hear a shorter wavelength and a higher pitch. If it's moving away from you, you'll perceive a longer wavelength, and as such, you will hear a lower pitch. Now this effect also occurs with electromagnetic radiation. You do have to be moving much faster in order to perceive this from electromagnetic radiation. And this is an effect we see in astronomy a lot. And also if you're dealing with, say, Doppler radar for weather observations. You send out a radio pulse, that radio pulse bounces off of a cloud and then is re-received by your device. The signal delay time in moving from the emitter to the cloud and back again tells you how far away that particular cloud is. Astronomers also use this to great effect to determine the distance to planets and the distance to stars. So here we can see and hear this particular effect. As we're standing here on the side of a racetrack, you should hear as a car passes by, and you can hear this from any particular recording of a Formula 1 race, for instance. You can hear the pitch of the car change as it passes the observer. Now the pitch that's heard right as the car passes by the observer is the really true pitch that you should be hearing. But as the car is approaching and receding, you should hear the change in the pitch from higher to lower. And that's the real effect of the Doppler effect. So, there are a couple of cases you have to take into account, and that is which direction is the observer actually moving? Is the observer moving towards or away from the source? Or indeed, is the source moving relative to the observer? For an observer moving towards the source, you'll have a wave speed relative to the observer of v prime is equal to v plus vo, here being the velocity of the observer, here being the velocity of the object emitting the sound. If the wavelength here is unchanged, v equals f lambda. But the frequency that's heard by the observer here will be increased by a factor of f prime equals v prime over lambda. So the new frequency due to the relative motion of the source will be f prime. This will equal v plus the velocity of the observer over lambda. As lambda is equal to v over f, for the observer moving towards the source, f prime will be v plus v0 over v. So essentially a ratio of velocities, velocity of the object, velocity of the observer. So v plus v0 over v times f. Now that's for an observer moving toward the source. For an observer moving away from the source, now v prime is v minus v0, or vo. The frequency heard by the observer will decrease in this case. So f prime will be v minus vo over v times f. That means we can take these two expressions and combine them together into one for simplicity's sake. And this means when we deal with the Doppler effect, we can reduce them down to a single equation and look at the sign convention. Now, here we have v plus vo, this is the velocity plus the velocity of the observer, over v plus vs. Here's the velocity of the source, here's the velocity of the observer. Here are our relative velocities. I'll show these in the next slide. And you can select the plus or the minus based on the motion of the object and the motion of the source times the base frequency, as it would be unchanged. What do I mean by this? And the best way to actually do this is to show it in an example. So here we have a submarine, submarine A, which is going to be moving at a speed of 8 meters per second, emitting a sonar wave at a frequency of 1400 Hertz. The speed of sound in water, let's say, is 1533 meters per second. A second submarine, which is sub B, which is this one over here, is going to be located so that both submarines are traveling directly towards each other. The second submarine, this one, is moving at 9 meters per second, so it's moving slightly faster than the one emitting the waves. So the question is, at what frequency is detected by an observer on sub B, on this one, as they approach one another? So sub A over here is moving and emitting a pulse This one is moving at 8 meters per second, this one at 9. Let's employ our formula. So here we're dealing with a situation where we want to calculate f prime, the frequency of an observer over here on this submarine. They will see this to be v plus VO, so this is positive on the top here because we are moving towards, over v minus Vs. This is relative to the source, this is relative to source, this is relative to observer. So observer is the submarine here, source is this submarine sub A here. If we substitute in, we will have 1,533 meters per second, here being the velocity of the wave, plus positive 9 meters per second, over 1533, again the velocity of the wave, here minus 8 meters per second. So here we're looking at the velocity of the source, here we're looking at the velocity of the observer. These two are moving towards one another. That means we'll have positive on the top and negative on the bottom. Multiply this by the 1400 Hertz, which is the base frequency of our submarine, and we'll end up with 1416 Hertz. Not a large change in this particular case. Now what you want to take away from this is not necessarily this final answer, even though the magnitude is important. But why did we assign the signs that we did? This is positive here because we're moving towards this observer, VO. This is negative here because the source is moving in this direction towards the observer. So this is relative to the source, this is relative to the observer. If this is positive, this will be negative in this case. So there's a part B here. Submarine A here is still doing the same thing, emitting its sonar and moving at 8 meters per second. As they move, the subs barely miss each other and pass each other. What frequency is detected on an observer riding on sub B as the submarines recede from one another? So again, submarine A at 8 meters per second passes submarine B at 9 meters per second. The frequency is unchanged and the speed of sound in water is unchanged. So again, we're looking at what frequency the observer on sub B detects. Again, let's use the same equation, but now we've got f is equal to v plus v0 over v minus vs times f. Substituting in, we can see now that this will be 1533 plus negative 9, and this will be 1533 minus 8. Here the two are receding from one another. So multiply by 1400, we'll have 1385 Hertz, 1385 Hertz, compared to our previous answer, of course, of 1416. So in the top case, we had one positive, one negative. In this case, we have both negative. Positive, positive, so we're giving a positive and a negative. Here we have a positive and a negative minus a negative to give us 1385. Now radio waves, of course, and things such as that used in meteorology or other subjects will be subject to the same Doppler shifting. Of course, to actually detect the Doppler shift of light, you do have to be traveling much faster as an observer, some good fraction of the speed of light. And the changing of an object's spectrum, if we look at a visual emission or absorption spectrum from an object somewhere out in the universe, will tell us immediately the direction of movement of that particular object. If an object's coming towards us, it's usually shifted towards the blue end of the spectrum, towards the shorter wavelengths. If an object is moving away from us, it's usually red shifted towards the longer wavelengths of the spectrum. The other thing we know is the greater the shift, the greater the speed. And that's basically the same as the change in pitch with a sound wave moving due to a moving sound wave. Objects moving towards you are higher, objects moving away are lower. And these are really the kinds of things that police use when they're trying to look at you using a speed camera. A pulse is emitted, hits your car, bounces off, and is received by their speed camera, allowing them to determine your speed based on the delay of the signal. The faster you're traveling, the shorter the delay. So when we're talking about redshift in terms of astronomy, if we measure a spectral line, that's an emission line that's given out by a particular star, we will see, say, a wavelength of 500.7 nanometers. If we measure the same line for a moving star, so we can simulate one in the lab, measure the same line for a star that's traveling through space, we'll end up with 502.8 nanometers. The wavelength from the star's spectral line is longer than it would be if it was in the lab in your stationary reference frame. This means a star is redshifted. If it's redshifted, we know this is occurring. The star is essentially moving away from the Earth. If the star is blue shifted, it's moving towards the Earth. Now, stars do move around. We see very, very high redshifts from very distant galaxies. Stars within our galaxy move away from us, some move towards us, all based on gravitation. We can also see such things as rotation. I realize in this diagram that Mars is spinning around its poles. Give me a break. It's the only picture I had handy. So as Mars is spinning around, if we use radar to look at one side of the planet, we should see that it's redshifted as it moves away from us. As Mars moves towards us on the other side, on this side, we should see the planet moving towards us and be blue shifted. So we can determine the rotation rate of planets in our solar system simply by looking at the light coming from them, or by using Doppler radar. While we're talking about light, and we'll come back to light later on, the speed of light is a constant. Now, we've seen v equals f lambda for other media that we've talked about. We've talked about the wavelength of, say, radio waves and things like that, possibly in the atmosphere. That means you have a velocity of v equals f lambda. If you see this equation, where c is equal to f lambda, c is usually referred to as the speed of light, and the speed of light is about 299.793 times 10 to the 6 meters, or usually abbreviated to about 3 times 10 to the 8 meters per second. The per second has gone off the slide here, unfortunately. Lambda, of course, is the wavelength, f, of course, is the frequency, but c here is different because this is the speed of light. The speed of light is the speed limit of the entire universe. If you ever have a calculation that goes more than 3, that gives you an answer with a velocity faster than 3 times 10 to the 8 meters per second, then you're pretty much wrong and should go back and do the calculation again. If you're not wrong, you discovered something fundamental that scientists have been missing about the universe, and I should take that idea and publish it for you. I'll mention you. I promise. This means that every sci-fi that you have ever seen, where spaceships travel at the speed of light and go to interesting and exciting places in the snap of a finger, really is a complete lie. C is the speed limit of the universe. Nothing travels faster than 3 times 10 to the 8 meters per second. And this is something we'll deal with a lot when we talk about electromagnetic radiation later on. When we're talking about photons, another equation to keep in mind, we have c equals f lambda. A related equation is E equals hf, and that's the energy of a wave, not necessarily just a photon here. And h here is Planck's constant, which is equal to 6.626 times 10 to the minus 34 joules seconds. You would, of course, have that given to you if you needed in an exam or in an assignment where you needed a formula sheet. F, of course, here is frequency. And this really relates energy to frequency. And of course frequency is related to wavelength. And what this means is the higher the frequency, the bigger the frequency, the higher the energy of a wave. And that means if we look at the entire electromagnetic spectrum, if we're down here in, say, radio waves. As we get to higher and higher, or shorter and shorter wavelengths, I should say, higher energies, the shorter wavelength means higher energy, more energy delivered per unit time. We go into microwaves. We can use this, of course, to vibrate water molecules and cook food. Going a little further, we go into the infrared. We then come into the visible light spectrum here. We're talking about 10 to the 15 Hertz there, and then we start leaving the visible light and going into ultraviolet. We're now getting into much higher energies. So now we're from ultraviolet into X-rays, and these things from here, from probably far UV through to gamma rays, are the things that are really damaging to most biological life forms, as we're looking at a lot of energy being delivered to tissues. So moving from ultraviolet and then moving into X-rays and gamma rays. X-rays and gamma rays are so high energy that they can actually penetrate solid matter due to their wavelengths. If we look at the Earth's atmosphere here, we can see here it says opaque, opaque, and transparent. Certain wavelengths actually make it through the Earth's atmosphere to the Earth. So in the optical, or here, over here in the radio, we can observe the entire universe. In the rest of these particular regions, we cannot actually see outside of our atmosphere so easily, and usually have to launch space observatories to do so. So to finish our discussion of waves, I'd like to discuss the idea of a shock wave. What is a shock wave? Well, a shock wave is when the speed of the source actually exceeds the speed of the wave. So this means really exceeding your local sound speed. And this means the object that's generating the sound is traveling faster than the sound itself that it's produced. And what that means is that you are passing the wavefront that's emitting your sound. And this gives an envelope of wavefronts in a cone configuration. Here's such a cone configuration of an object here that's moving with a velocity vs of its source. So the envelope of wavefronts gives us a sine theta for this particular angle of v over vs. Where vs is the source and v is the velocity of the wave. So here's, say, a bullet moving through a fluid, that fluid usually being air for our cases, and here's this bullet moving through, and as you can see there is a shock front set up here as the bullet exceeds the speed of sound, and you can see the angle that's set up in that wave as this bullet exceeds the local sound speed. There's also a lot of turbulence generated behind the bullet as the fluid moves around it. So this effect is referred to as a shock wave. So anytime you see a shock wave referred to, this is what it means. We mean a shock is set up by an object exceeding the local sound speed. And this is the kind of effect that causes the sonic boom from aircraft that break the speed of sound, or in some cases the double sort of bang sound that can be heard from very high energy ammunition when a bullet is fired. So when we look at shock waves, the ratio Vs over V is referred to as a Mach number. So the relationship between the Mach angle and the Mach number is given by V times T over Vst, or V over Vs. The theta that we're referring to is this particular angle. And as you can see, this is quite accurate when we're talking about a vehicle exceeding the speed of sound. Here a plane is exceeding the speed of sound, setting up a shock wave, and we have a lot of energy expended in this particular shock wave, and that's causing this condensation in the wake of the vehicle. Now Vs over V is usually given in terms of a Mach number. A plane that's flying at about Mach 2.4 has a speed that's almost equal to its Mach number of 2.3 times the speed of sound. So that means if you're going Mach 2.4, and you often hear these kinds of words thrown around, it's going 2.3 times the speed of sound in the air it's flying through. I say in the air it's flying through because there is a certain dependence on density of air. That means the higher in the atmosphere you are, the easier it is to actually exceed the speed of sound. So flying faster than sound at high altitude is easier than flying faster than sound at ground level, as we already discussed. Now when we're looking at a shock wave, we have our conical shock wave produced, and here's our bullet again, this time in colour, moving from the left to the right. And that carries an enormous amount of energy along the surface of this cone, giving you these massive pressure variations in a very condensed space, hence that enormous cone that was produced by the aircraft in the previous slide. So our ratio is the object speed over the speed of sound. And this is something we saw here, Vs over V. Velocity of source over V. And that gives you your Mach number. Generally, subsonic systems are Mach numbers less than 1. Transonic, when you're approaching 1. Anything greater than 1 is supersonic. And then we can get into the hypersonic once we start dealing with Mach numbers greater than 5. Not only are we dealing with Mach numbers of moving objects, if we're talking about shock waves, we can also look at shock waves in terms of an explosion or massive release of energy, letting a wave move through the atmosphere. If anyone looks at the recent explosion that occurred in Beirut due to the poor storage of nitrates, you can actually see the shock wave expand from this particular explosion. This explosion was very, very well observed, as people with cell phones and security cameras and everything around the city actually showed us the propagation of this particular wave. A lot of nuclear explosions that have been set off in history, specifically the tests of atomic bombs, show us large-scale shock waves. In fact, these shock waves can be seen here throwing, at this bottom picture here, throwing actual aircraft carriers. Sometimes these shock waves are natural. Here's a particular artist's impression of a shockwave created by the object that created the Tunguska incident. Please stop me and talk about this if you wish to, but I won't divert the lecture to talk about it. This shockwave was set up in the front of an object and hit a large region of Siberia, flattening the landscape and leaving thousands of kilometers of trees flat on the ground, very similar to the effect we saw with the Hiroshima and Nagasaki atomic bombs. Shockwaves set up in the atmosphere, of course, are very, very similar to those set up by aircraft and bullets, but on a much larger scale. On the larger scale, we see stellar shockwaves. These are shockwaves set up by such things as exploding stars, type 2 supernovae. When this happens, shells of material are ejected from the star, followed by a second wave of material which exceeds the speed of the first, overtaking the first one and causing the excitation of the first wave and giving these incredibly bright, vivid colors in a great big bubble. The reason that you're seeing more light here, more excitation on the edges, is because you're looking through more material on the edges than you are in the center. And in terms of astronomical objects, looking at something like Eta Carina, a star which exploded in 1843 and created a nebula of its own. A rapid shock wave headed through the nebula and excited the nebula, and actually ended up with several successive shock waves overtaking each shell and causing massive excitation to give us this really nice kind of stellar fireworks show. So that's shock waves on the large scale. when we are dealing with something in space, we're still dealing with the same physics we are when we're dealing with our atmosphere. But of course, when we're dealing with a nebula or something like this in the vastness of space, we're dealing with much lower pressures and much lower sound speeds. But the physics is still the same.